I poured a $1 cherry soda from Shore, 5-minute swarm. I opened a bottle of off-brand cherry soda and poured 12 ounces directly into the shallows of a farm pond. The water was stained brown from tannins and runoff. Visibility was less than 6 inches. I didn't use a rod. I didn't bait a hook. I stood on the bank with a stopwatch and waited. At 4 minutes and 41 seconds, the surface erupted. Bluegill, green sunfish, and small bass converged on the entry point in a feeding frenzy so aggressive that dorsals and tails broke the waterline. I counted at least 30 individual fish in a zone no larger than a trash can lid. They weren't chasing bait. They weren't responding to movement. They were locked onto a chemical signal that had turned a 3-foot radius of muddy water into a kill zone. The soda cost 99 cents at a gas station. Sugar doesn't behave in water the way most people think it does. When you pour a high-fructose corn syrup solution into a pond or creek, it doesn't instantly dissolve into invisibility. It's denser than water. It sinks. And as it sinks, it forms a viscous plume that spreads outward in slow, curling tendrils, carrying with it a molecular signature that freshwater fish have been evolutionarily programmed to recognize as food. Here's why. In natural aquatic ecosystems, sudden pulses of dissolved sugars occur in very specific circumstances. When fruit falls from overhanging trees and begins to ferment, when cicada emergences die off en masse and their bodies break down, when algae blooms collapse and release their stored carbohydrates into the water column. These events trigger feeding frenzies. Fish don't encounter concentrated sugar often, but when they do, it means an abundance of easy calories. Their neurochemistry is wired to capitalize on it immediately. High-fructose corn syrup, the primary sweetener in cheap sodas, is a near-perfect analog for the sugars released during organic decomposition. It's a blend of glucose and fructose in roughly equal proportions. When it enters the water, it doesn't just smell like sugar. It behaves like sugar. It sinks. It lingers. And it broadcasts a feeding opportunity to every chemoreceptor within a 50-foot radius. The test site was a 2-acre pond in central Missouri. Water temperature, 76 degrees Fahrenheit. Dissolved oxygen, 6.8 parts per million. The pond had been stocked with bluegill, largemouth bass, and channel catfish. There was moderate algae growth along the south bank and submerged timber along the north side. I chose a shallow flat on the east shore, where the depth ranged from 18 inches to 4 feet. I poured the soda in a single continuous stream, emptying the bottle in approximately 8 seconds. The liquid was bright red. As it hit the surface, it dispersed into a pink cloud that immediately began to sink. I could see it for the first 6 inches of descent. Then it disappeared into the tannin-stained water below. I set a stopwatch and watched the surface. For the first 3 minutes, nothing. The water remained still. No surface activity. No subsurface flashes. Then, at 3 minutes and 22 seconds, I saw the first dorsal fin cutting toward the pore site. A bluegill, roughly 5 inches long. It circled the area twice, then dove. At 4 minutes and 9 seconds, 2 more bluegill arrived, then a small bass, then 3 more bluegill. By 4 minutes and 41 seconds, the surface was boiling with fish. They were packed so tightly that their bodies collided. They weren't feeding on insects or plankton. There was nothing visible for them to eat. They were feeding on the water itself, gulping mouthfuls, filtering the dissolved sugars through their gills and buccal cavities, absorbing the glucose directly. This behavior is called osmotrophic feeding. It's rare in fish, but it occurs when dissolved organic carbon concentrations spike above normal background levels. The fish don't need to see prey. They don't need to chase it. They simply position themselves in the thickest part of the chemical plume and drink it in. I repeated the test with 4 different sodas to determine if the response was flavor-specific or sugar-driven. I tested cherry cola, orange soda, grape soda, and lemon lime. All were off-brand. All cost between 99 cents and 1.29 per bottle. All contained high-fructose corn syrup as the primary sweetener. Cherry Cola. Swarm began at 4 minutes, 53 seconds. Orange Soda. Swarm began at 5 minutes, 12 seconds. Grape Soda. Swarm began at 4 minutes, 28 seconds. Lemon Lime. Swarm began at 6 minutes, 4 seconds. The differences in response time appeared to correlate with the density and viscosity of the soda. Grape Soda, which had the highest sugar content at 44 grams per 12 ounces, produced the fastest response. Lemon Lime, which had the lowest at 37 grams, produced the slowest, but all of them triggered a feeding response. Every single one. I also tested this in moving water. I poured cherry soda into a slow creek with a current speed of approximately 0.4 feet per second. The plume stretched downstream in a visible red ribbon for the first 20 feet, then faded from view. I walked the bank and observed the water. At 7 minutes and 18 seconds, I saw the first boil. A carp, estimated at 3 pounds, was holding position in the current lane directly downstream of the pour site. Its mouth was opening and closing rhythmically. It was filtering. I continued walking. At intervals of 15, 30, and 45 feet downstream, I observed additional fish holding in the current, all facing upstream, all feeding. The sugar plume had extended at least 100 feet from the point of entry, and every fish in that corridor had locked onto it. Here's the chemical breakdown. High-fructose corn syrup consists of monosaccharides, simple sugars that don't require enzymatic digestion to be absorbed. When dissolved in water, these molecules remain in suspension longer than complex carbohydrates because they don't aggregate into larger particles. They disperse slowly, creating a gradient that fish can follow back to the source. The artificial flavoring compounds in soda, primarily esters and aldehydes, add a secondary attractant layer. Cherry flavoring, for example, contains benzaldehyde, the same compound found in decaying stone fruits. Grape flavoring contains methylanthranilate, a compound that occurs naturally in Concord grapes and certain aquatic insects. These aren't random chemicals. They're molecular mimics of food sources that fish already recognize. But the sugar is the driver. In a controlled study published in 2007, researchers at the University of Minnesota found that bluegill and crappie exhibited increased foraging activity when exposed to glucose concentrations as low as 0.5 parts per million. At concentrations above 2 parts per million, the fish abandoned all other food sources and focused exclusively on the sugar plume. A 12-ounce soda contains roughly 40 grams of sugar. When poured into a small pond, that creates a localized concentration well above the threshold for triggering osmotrophic feeding. The fish aren't tasting sweetness. They're detecting caloric density, and they're responding the way their ancestors did when a mulberry tree dropped its load into the shallows 10,000 years ago. I attempted to replicate this effect using pure granulated sugar dissolved in water. I mixed 4 tablespoons of table sugar into a 12-ounce bottle of tap water, shook it until dissolved, and poured it into the same location where I had previously poured the soda. The response was muted. Fish arrived, but the swarm was smaller and took longer to form, nearly 9 minutes instead of 5. The difference, I suspect, is viscosity. Soda contains phosphoric acid, caramel coloring, and other additives that increase its density and slow its dispersion. Table sugar dissolved in water is less dense and disperses more quickly, creating a weaker scent plume. The lesson: it's not just the sugar, it's the delivery system. The soda's engineered formulation, designed to maximize sweetness and shelf stability, happens to also maximize its effectiveness as an aquatic attractant. I also tested diet soda as a control. Diet cherry cola, sweetened with aspartame and acesulfame potassium instead of sugar, was poured in the same volume and location. I waited 15 minutes, no swarm. A single bluegill passed through the area, showed no interest, and continued moving. The artificial sweeteners, which humans perceive as intensely sweet, are not recognized by fish chemoreceptors. They produce no glucose signature, no osmotic draw, no feeding response, The fish don't care about flavor. They care about energy density. And artificial sweeteners provide none. By the end of the field session, I had documented 12 separate pores across 3 different bodies of water. Every pore that contained real sugar produced a measurable aggregation of fish within 6 minutes. The average swarm size was 23 individual fish. The average duration of the swarm was 11 minutes before the sugar concentration dropped below the threshold and the fish dispersed. Total cost of materials, $11.88 for 12 bottles of soda. That's 99 cents per controlled feeding frenzy. Compare that to the cost of a single jar of commercial Chum, which runs between $12 and $18 and is marketed as a proprietary blend of fish oils, amino acids, and scent enhancers. The soda outperformed it in every measurable category: speed of attraction, density of aggregation, and cost per application. The mechanism is simple. Pour the soda, wait 5 minutes, cast into the swarm. The fish are already in a heightened feeding state. Their chemoreceptors are saturated. Their threat assessment systems are suppressed. They're competing with each other for position in the plume. When a bait enters that zone, it doesn't get inspected, it gets attacked. You don't need to match the hatch. You don't need to twitch the lure. You don't need to finesse the presentation. The fish are already convinced there's food in the water. You just need to give them something to bite.